Okay. So last week we got through Newton's laws, and I kind of rushed through everything with Newton's laws, but I feel like we got through it good enough. If you feel like you want me to explain it more, I can definitely do that. Otherwise, I think I'll just kind of move on from Newton's laws and talk about momentum. And if we have time, then electricity and magnetism. So momentum is kind of the last piece of the puzzle when it comes to talking about kind of force and motion and all of that kind of stuff that we were talking about last week. So momentum is very similar to force, or similar to inertia, but momentum is just simply defined as product of mass and velocity. In other words, if you take the mass of an object and you multiply it by how fast it's going, that gives you momentum, right? So if we take a car, we would find out how much the car weighs, take that measurement, multiply it by how fast it's traveling, and that would give us the amount of momentum, right? So when it comes to momentum, we don't have much to talk about because it's so similar to some of the stuff we talked about last week. The biggest thing, just like we've talked about with energy and mass when it comes to chemical reactions, momentum is conserved. In other words, if we take let's take a car crash. That's kind of a dark. Let's take a collision between two cars. Right? The amount of momentum between the two vehicles at the beginning or before the collision is going to be the same as afterwards, right? And so maybe instead of talking about a car crash, maybe if we just talk about like, pretend these blocks are like our cars. So let's say these blocks are traveling whatever speed. We're not going to use a lot of math today just to kind of simplify everything. But these two cars are traveling, or two blocks are traveling on a collision course. They have a certain amount of momentum. When they hit, one will hit, and one might absorb more momentum than the other. But in the long run, the two objects are always going to have, when you add them together, they're going to have the same total amount of momentum. Right? So I don't feel like we need to go over that anymore. So if you can just remember, momentum is mass times velocity. That's all you need to know. So let's maybe look at, before I get into kind of a totally new topic, let me pull up like maybe one or two practice questions that kind of talk about momentum and kind of motion and force, and then I'll go into kind of a brand new topic. So let's see. I think I just want to do a couple of, we're going to skip around most of these, but I think I want to do number 4. It talks about momentum specifically. So let's do number 4, and then we might do number 5, and then we're going to move on. So number 4 just says, select the phrase from the choices below that correctly complete the statement, or completes the. So if we look down at the bottom, down here, right, here are our 3 choices. So decreases when its velocity decreases, increases when its velocity increases, or decreases when its velocity increases. So let's read the paragraph and kind of see what the fill in the blank they're looking for. So it says, a car is traveling at a velocity of 30 miles an hour across a narrow bridge when it is approached on a collision course by another car traveling at 30 miles per hour. Two cars traveling at 30 miles per hour towards each other, going to each other. the momentum of each car is propelling it forward, and there is no way to completely avoid an impact. So these two cars are going to hit each other no matter what. Because the momentum of the car blank, each driver should attempt to decrease his car's speed to lessen the severity of the impact. Let's go ahead and read that last sentence with each of these fill-ins, and we'll kind of see what makes sense. Because the momentum of the car decreases when its velocity decreases, each driver should attempt to decrease his speed. Because the momentum of the car increases when its velocity increases, each driver should attempt to decrease their car's speed. Because the momentum of the car decreases when its velocity increases, each driver should attempt to decrease their car's speed. Okay, so definitely this third one doesn't make sense. Okay? Momentum doesn't decrease when velocity increases, right? Think about that. And then, like we talked about last week, think of momentum like something hitting. So if something has more momentum, it's going to hurt more, or you're going to feel it more if it hits. Whereas if something has less momentum, it's not going to impact you as much. Okay? So if velocity is increasing, right, traveling faster, then momentum is also increasing. So both of these first two options are true statements, right? Momentum does decrease when velocity decreases. Momentum does increase when velocity increases. But which of them applies to this scenario, right? If we have two cars traveling towards each other, should they increase their speed? Probably not, right? So because the momentum of the car decreases when its velocity decreases, each driver should attempt to decrease the car's speed to lessen the severity. So that's probably all we need to do in terms of talking about momentum. Let's go ahead and look at number 5. I just think number 5 is kind of interesting and talks about some stuff we talked about last week. And I know everybody here was in class last week. So let's just do number 5, and then I'm going to move on to a brand new topic for the last part of class. Let's see. So let's read number 5 and do that one. 5. So they give us a paragraph and they give us a graph, right? And we want to know, what does the graph show us? A, an object that is not moving. B, an object that has a constant speed. C, an object that is accelerating. Or D, an object that is. So let's first read the paragraph real quickly, and then we'll look and see what the best answer is for the question. So the paragraph says, graphs are often used to convey information about motion. One type of motion graph shows distance and time. Distance is measured from a particular starting point. If the distance graph has a straight horizontal line, the distance is unchanging and the object is not moving. If the distance graph has a straight line with an upward slope, the distance is changing at a constant rate. This means that the object is moving at a constant speed. If the distance graph is a curve, the object is accelerating or decelerating, depending on the shape of the curve. Okay? So we probably could have answered this question without even reading the paragraph, but basically what it's saying is that graph down there, right? We have distance, which is straight up and down, right? We have time, which is the horizontal. So if we have a totally flat line, then they tell us that means the object isn't moving. It's not gaining any distance. If that line is staying flat, then time is elapsing, but you're not traveling any distance, and so that object isn't moving. Then it goes on to say, if you have a straight line with an upward slope, meaning like that, then the distance is changing at a constant rate. In other words, for every certain amount of time, you are traveling a certain amount of distance. It's going, and so it's constant, right? So that means that you're traveling at a consistent speed, or your speed isn't changing. It's just you're moving, but you're moving at a steady rate. And then lastly, it's saying if the graph is a curve. So if it was an upward curve or a downward curve, then you would be moving. You'd be moving at either an increasing rate. If it was an upward arcing curve, you'd be accelerating. Or if that curve was decreasing, right, going down, that would mean you're slowing down and coming closer to the stop. So we've kind of answered our own question here. What does the graph above show? A, an object that is not moving. We know that's not true. Moving or not moving would look like that. An object that has a constant speed, an object that is accelerating, or an object that is decreasing or decelerating. We know straight line ascending in a positive direction, we know it's an object traveling at a constant speed. So the answer is B. Okay. So that was a pretty easy question, but I just kind of wanted to go over a couple questions to give a little bit of a break before I kind of totally switch gears and go to something. So I was mentioning this earlier before class officially started, but this is kind of the last day of going over physical science. And then tomorrow I'm going to do some review questions. And then Wednesday, we're going to start a brand new topic in science. So the last thing left to go over in is electricity and magnetism. So when we talk about electric charge, remember when we talked about atoms and their makeup and how they have positive protons and negative electrons? That's essentially how electricity works, right? You get this electrical charge because you have these separate or opposite charged particles that are built into matter, right? So you have electrons that have negative charges and protons that have positive charges. Particles with like charges repel each other. So think batteries, you know? When you put a bunch of batteries in, say, a flashlight or whatever it is, right? You put the positive end up against the negative end and so on and so forth. If you put negative to negative, what happens? Nothing. You don't get any electricity. You're not generating any electricity because that battery is made so that the like ends repel each other, but if you put it around and you have the unlike ends, they're attracted towards each other and electricity flows through those batteries. So when we talk about electricity, there are a few things that I kind of want to point out, right? First is there are some different types of electricity. So you've heard of static electricity. That would be electricity, or that's temporary. So electrons are temporarily pulled away from the atom, creating a short electric charge, but then it goes away, right? So if I had any hair, right, I could rub my hair crazy and get my hair to like stand up, but my hair is pretty short, so don't have that luxury. But for those of you that do have some hair, right, if you took a balloon, right, and rubbed it against your head, pull the balloon away, your hair, right? That's static electricity. Or when you pull your clothes out of the dryer and they're all stuck together, you pull them apart and you hear the crackling, and, right? That's static electricity. Temporary bursts of electricity. It's not a consistent form of electricity where you couldn't power a appliance with static electricity. That wouldn't work very well, right? So electric current is more consistent and can be sustained over a longer period of time. So electric current is when you have movement of charged particles, right? And that's usually electrons. Again, don't get hung up on remembering some of these real specific things. I just want you to think big picture. And then when we talk about electric current, there are two main types of electric current. One would be direct flow and one would be alternating. Okay, so direct current is stuff or is electricity that flows in one direction. In other words, there's a starting point and an end point. Right? If we have a flashlight and it has 3 batteries in it, and those batteries are chained one to the other, right? then that electricity is only flowing in one direction. In other words, there's the little conductor at the start, and it's next to this battery, and the electricity flows through this battery to the next battery, to the next battery, to the light, and then projects the light. Right? But electricity isn't flowing back the other way. In other words, electricity doesn't then get turned around from the light bulb back through the batteries back to the cell. Right? It's just flowing one direction. Whereas when we talk about alternating current flows back and forth. So that's why when we have electrical wiring, there are, if you were to cut open an electrical wire, right? So there's like a casing around the outside, but then there's usually two, at least two, and sometimes three because there's a grounding or a grounding wire. There are two active wires within that electrical wire. And that is because one, the electricity is flowing one way in one of those wires, and it's flowing the other way in the other wire. Right? Electricity is going back and forth when we're talking about electrical wiring, or when we think of things that we plug in. That's all that stuff is using alternating current. In other words, there's always electricity flowing in both directions. All right, so kind of the last bit here, when we're talking about electricity, the big takeaway here that I want you to remember is there are some different types of materials as it relates to electricity that are either helpful or useful when we're talking about electricity. So the first thing is conductors. So conductors are the term for materials that allow electrons to move freely from atom to atom. In other words, they're good at generating electricity. They allow electricity to flow, right? And those are generally metal. Okay? So what's the reason why we don't go outside in a lightning storm and hold up a metal rod? Because metal is a conductor. Electricity is attracted to that, and electricity flows through it actively. So if we're outside holding a metal rod in a thunderstorm, and lightning hits our rod, that electricity hits the rod, and that rod transfers that electricity to our hand, and we feel that. So why electrical wiring, actual wires, are made up of metal, because they are good conductors or creators of electricity. They help electricity flow freely. Then on the other side of that, we have insulators, and insulators are the opposite. Insulators are materials that do not allow electrons to flow or do not allow electricity to transfer freely, right? And that would be stuff like rubber or plastic. So again, the reason electrical wires are usually coated in rubber or plastic is because electricity doesn't flow through that, right? Inside that rubber casing, there's metal wires, and the wires are metal because they conduct electricity. But then they're coated in rubber so that we can go and grab the wire and not shock ourselves. Right? If we were to cut that rubber wire open and just grab that metal wire while it's actively generating electricity, we'd shock ourselves. Okay? So insulators are material that do not allow electrons to flow freely. Okay? So another example would be, trying to think of an example. Like in the case of a thunderstorm, if we were to go outside and stand under a plastic tarp, we wouldn't want that. That's a really bad example, but you get my point. Is that electricity might hit that, but it's not going to transfer through, right? Or in other words, if let's say this. And this is, again, not something I would recommend doing, but if we have a metal rod, right? If that metal rod has a rubber grip on it, and we go out and we hold it up, right? Again, we shouldn't do that. We don't want lightning striking 5 feet away from it. But if we had a rubber grip on that, that rubber doesn't allow electricity to flow through it, so that lightning would hit the pole, and that pole would be filled with electricity. That rubber grip would stop that electricity from transferring from the pole to us. And then the last category here, is called semiconductor, and you figure out kind of where they fall in between. They're not conductors, they're not insulators, they're kind of in the middle. So semiconductors are substances whose ability to conduct electricity is halfway between a conductor and an insulator. Electrons can move back and forth, generating electricity at a lower, more controlled level. So things like metalloids, and we refer to metalloids as things that aren't metal but have similar properties of metal, like silicon, are common semiconductors. And you see semiconductors a lot in like complicated electronics. So like a computer, you don't see a lot of raw metal inside that because you don't want electricity flowing, totally freely inside the inner workings of a computer. You want there to be electricity because you need that, but it needs to be regulated. And so you'll see lots of silicone or things like that that are used in stuff that requires electricity, but it may need it to be a more controlled, lower amount of electricity. Okay? So conductors, insulators, and semiconductors. So with that said, let's stop there. I'm going to pull up a couple questions that deal with that, and then we will call it a day. And again, I will come up with some review questions to look at that cover all of the physical science stuff we've been talking about the last couple of weeks, and then move on to a totally new. So let me pull up some more questions. Down here. So I'll give you an easy one to start with. So let's look at number 2. And so we'll start with 2 and 3. So obviously we'll go and do them one at a time, but let's do number 2 first. And number 2 says, what is the reason copper and aluminum are used for electrical wiring? A, copper and aluminum are conductors. B, copper and aluminum are insulators. C, copper and aluminum are semiconductors. Or D, copper and aluminum are magnets. Remember, if we're trying to generate electricity, right, what are we looking for? Or do we want conductors, insulators, or semiconductors? Well, we for sure can throw out D, okay, because being magnetic doesn't factor into this question. So D isn't what we're getting at. So is it A, B, or C? And remember, insulators restrict electric flow, so we know B is not going to be right. Semiconductors were what we just talked about, which is it allows electricity to flow at a lower, more regulated level. But when we're talking about electrical wiring, we need a lot of electricity to flow quickly and freely. And so A is the right answer. Copper and aluminum are conductors. So let's look at a little more, a little higher level. Number 3's got a little more going on. So it says based on the information, but all the information we've talked about should be plenty for you to answer this question. It says, which of the following devices is most likely to use direct current? So you weren't here when we talked about it. The 2 different types of current are direct and alternating. Okay? So direct current is electricity starting here and just traveling in one direction to an endpoint, whereas alternating current is electricity going back and forth and back and forth. So our options are A, washing machine, B, a desktop computer, C, a toaster, D, a flashlight. So remember, typically anything that is using electrical wiring, in other words, if you have to plug it in, chances are it's using alternating current because electrical wiring is electricity going in both directions. The washing machine plugs in, not the right answer. A desktop computer, typically plugged in, right? Not a laptop, but a desktop that plugs in using alternating current. C, the toaster, same thing. Plug it in. So the answer is D, a flashlight, right? Flashlight uses batteries, which was the one example we talked about when we talk about direct current, because you plug those batteries in a chain, and the electricity is generated here, and it runs through this battery, to the next battery, to the next battery, to the light on the flashlight, right? It doesn't go back the other direction. So your answer would be, all right, and lastly, when you zoom out a little bit, we're going to do questions 5 and 6. So first, let's look at number 5. Number 5 says, an electrical circuit is a complete pathway for the flow of electric current. It consists of a source of electricity, such as the battery, wires along which the current travels, devices called resistors, powered by the current, and often a switch to start and stop the flow of current. Okay, so they kind of give us 4 pieces, and then they give us an example of a circuit down here, right? And we've got switch, light bulb, wire, 9-volt battery. First question, number 5, just asks you to identify the resistor in the circuit. So if we go through, and you might still not even know what a resistor is, even if you read it up there and you weren't sure what they were asking. Process of elimination, we should be able to answer this one pretty easy. Okay? So the 4 components of an electric circuit are a source of electricity, such as a battery. So battery, that's the first thing. That's not a resistor because it's the source. Then it says wires along which the current travels. So wires, so it's not this. So it's not battery and it's not wires. It says devices called resistors powered by the current. So that's what we're looking for. So it's either the light bulb or the switch. And lastly, it says often there is a switch to start and stop the flow of electricity. So that's the 4th component. So by process of elimination, we know it's not the battery, it's not the wire, not the switch. So the resistor here is actually the light bulb. The light bulb is what is acting as the resistor in this. In other words, that's the device being powered by this electricity. All right, so a little more complicated question, and the last question of the day, number 6. Let's read through it. Number 6 says, a student was asked how the current in the circuit shown above could be stopped without using the switch. He answered the only way to stop the current was to disconnect the battery. What was wrong about the student's response? Okay? The student says the only way that we can stop the flow of electricity in that circuit is to totally disconnect the battery. Now, we're looking for what was wrong with that response. A, disconnecting the battery will not stop the current. B, removing the fuse will also stop the current. C, disconnecting the light bulb will also stop the current. Or D, there is no way to stop the current without using the switch. Okay. What do we think? Well, we know it's not A. Disconnecting the battery will not stop the current. The student was correct when he answered that disconnecting the battery would stop the current. Where he was incorrect is it's not the only way. Okay? So A is wrong, not because it's not true, but because it's not the only way. Okay? B, removing the fuse will also stop the current. Okay? Now, where do we see mention of any kind of fuse in there? I don't see one. Okay? So be careful not to fall for stuff that doesn't apply to or that doesn't come directly from the diagram. I don't see anything about fuses up there, so throw it out. C, disconnecting the light bulb will also stop the current. Okay, sounds like potentially the right answer. Or D, there is no way to stop the current without using the switch. Well, we know D is wrong because we know at the very least you can use the switch or you can unplug the battery. But C is the right answer here because disconnecting the light bulb also stops the current. So again, not an overly difficult answer, but kind of an odd question, and similar to something you would expect to see on the test, where you get a picture or a diagram, and you're asked to answer a question about it and apply it to something a little bit different, or something that's not specifically mentioned. So that's all I've got for physical science, and tomorrow, again, we will run through some practice questions reviewing physical science. So if you've missed anything from the last couple of weeks, I'll try to recap some of the stuff we talked about and do some questions that help answer anything we might be needing to go over with physical science. And then Wednesday, we'll start a brand new science topic.